When people hear different storm names like hurricane, typhoon, or cyclone, it can sound like totally different weather events. But at the core, these are mostly regional labels for the same physical system, a rapidly rotating tropical storm built around low pressure, organized thunderstorms, and strong inward-flowing winds that spin around a center. The name changes with geography. In the Atlantic and the northeastern Pacific, it is called a hurricane. In the northwestern Pacific, it is called a typhoon. In parts of the Indian Ocean and South Pacific, it is generally called a tropical cyclone. So the terminology is regional, but the engine is shared. That distinction matters because it helps us compare storms globally rather than treating each basin as a separate mystery. On average, about 80 to 90 named tropical cyclones form worldwide every year, and more than half of them intensify to hurricane-force winds. So this is not a rare edge phenomenon. It is a recurring global process tied directly to ocean temperatures, atmospheric structure, and Earth's rotation. To understand how a tropical cyclone works, picture a heat engine sitting on warm ocean water. The sea surface provides the raw fuel through evaporation. Water vapor rises, cools, and condenses into clouds and rain. That condensation releases latent heat into the storm's core, and this extra heat lowers pressure further and strengthens rising motion. Lower pressure then pulls more air inward at the surface, feeding more moisture into the system. In other words, the storm reinforces itself through a feedback loop. Warm water drives evaporation, rising moist air releases heat, pressure falls, winds intensify, and stronger winds can increase moisture transport into the core. This is fundamentally different from many mid-latitude storms, which are powered mainly by horizontal temperature contrasts between air masses. Tropical cyclones are less about warm air colliding with cold air and more about ocean heat being converted into organized wind and rainfall. If the ocean is warm enough and the environment supports vertical development, the process can scale from a disorganized disturbance to a mature cyclone remarkably fast. A mature tropical cyclone has structure, not chaos. At the center is a low-pressure core, often with a relatively calm eye in stronger storms, surrounded by an eyewall where winds and rainfall are usually most intense. Outside that core, spiral rainbands curve inward like giant atmospheric conveyor belts, transporting heat and moisture toward the center. Wind does not simply blow straight into the middle because Earth's rotation bends moving air, creating the characteristic spin. Air converges at low levels, rises in deep convective towers, then spreads outward aloft. This vertical circulation lets the storm continuously vent mass at the top while drawing in more fuel near the surface. Typical diameters can range from around 100 to 2,000 kilometers, so these systems can be compact and violent or sprawling and region-shaping. Size also matters for impacts. A smaller storm can still be extremely intense near its core, while a larger one can deliver broader wind fields, wider rainfall coverage, and more expansive coastal effects. Intensity and size are related but not identical, and risk decisions must account for both. One of the most important and least intuitive facts is where tropical cyclones usually do not form, very close to the equator. Most rarely develop within about 5 degrees latitude of it. The reason is rotational leverage. The storm needs enough Coriolis effect, created by Earth's rotation, to help organize inward-flowing air into a sustained spin around a center. Near the equator, that rotational deflection is too weak to support stable cyclonic structure in the early stages. So even with warm water present, the system often cannot tighten into a coherent rotating core. This is why genesis zones cluster in tropical and subtropical belts away from the equatorial line rather than directly on it. It also explains basin patterns. Some regions repeatedly produce storms because ocean warmth, atmospheric instability, and rotational support overlap there. Others are much less active because one or more ingredients are consistently missing. Understanding these spatial rules helps forecast agencies and coastal planners prioritize surveillance corridors long before storms get named. Not all ocean basins are equally favorable. For example, the South Atlantic is notably quiet compared with the North Atlantic or Western Pacific. That scarcity is linked to environmental inhibitors like stronger vertical wind shear and weaker large-scale convergence patterns. Wind shear, the change in wind speed or direction with height, can tilt and disrupt a developing cyclone, separating its low-level center from deep convection and preventing efficient heat engine coupling. By contrast, parts of the Atlantic and Caribbean regularly see ingredients align through mechanisms such as atmospheric instability and regional wave disturbances that can act as seedlings for storm development. The point is that cyclone formation is never about warm water alone. It is a multi-ingredient recipe: warm sea surface, moist and unstable mid-level atmosphere, low enough wind shear, sufficient rotation, and a pre-existing disturbance to organize. Remove one critical piece and development may stall. Put them together in the right sequence, and a disturbance can rapidly transition from a rain cluster into a named system with dangerous winds and flooding potential. Once a tropical cyclone strengthens, people often focus only on peak wind speed, but wind is just one hazard channel. The storm's rotation and pressure gradient generate destructive gusts capable of structural damage, vegetation loss, and infrastructure failure. At sea, persistent winds transfer energy into waves that can become enormous and chaotic near coastlines. Meanwhile, reduced central pressure and onshore wind push ocean water toward land, producing storm surge, often the deadliest coastal impact. Surge is not just a big wave, it is a large-scale rise in sea level at the shore, which can flood neighborhoods, roads, ports, and critical systems even before the eyewall arrives. Heavy rainfall compounds this by filling drainage networks from above while surge blocks runoff paths from below. In stronger systems, embedded tornadoes can also occur, adding localized but severe damage corridors. So cyclone risk is layered: wind, surge, waves, rain, and occasionally tornadoes interacting in the same event. Good preparedness requires treating the storm as a compound hazard, not a single-number wind category. Coastal zones are typically hit hardest, but the idea that inland regions are mostly safe is misleading. The ocean-powered core weakens over land because the storm loses direct access to warm water fuel, yet dangerous impacts can continue far inland through rainfall and river response. Tropical cyclones can pull moisture from a huge surrounding area and concentrate it into precipitation over a much smaller target zone. That means rainfall totals can greatly exceed what local atmospheric moisture content alone might suggest at a given moment, because the storm is continuously importing and replenishing humid air. In practical terms, this supports multi-hour or multi-day extreme rain events, and those can occur dozens of kilometers from the coast. Rivers rise, soils saturate, overland flow accelerates, and water control structures get overwhelmed. Even if wind damage decreases inland, flood damage can intensify downstream as runoff propagates through watersheds. This is why evacuation and emergency planning cannot stop at shoreline maps. Inland communities need flood-focused preparedness, especially where terrain, drainage, and land use amplify runoff concentration. Rainfall behavior in tropical cyclones deserves special attention because it often drives long-duration disasters. Spiral rainbands can train over the same region repeatedly, meaning one burst of heavy rain is followed by another before water levels recede. Urban surfaces reduce infiltration, rural basins may already be saturated, and reservoirs or channels can lose buffering capacity quickly. The result is cascading flood modes, flash flooding in small catchments, urban inundation from overwhelmed drainage, then broader river flooding that peaks later and lasts longer. This time lag effect creates a dangerous perception gap. Residents may think the worst has passed when wind diminishes, while hydrological risk is still climbing. Emergency communication needs to reflect that sequence clearly. Wind danger can peak first, but water danger can persist or even worsen after landfall and after the storm center moves away. The same cyclone can therefore produce multiple emergency phases across different locations and times. Understanding this staggered timeline improves response coordination, resource allocation, and public behavior during and after impact. Climate change is now a critical context for interpreting cyclone risk. Warmer oceans increase the energy available to these storms, and a warmer atmosphere can hold more moisture, which can intensify rainfall potential. Scientists have found that climate change can exacerbate impacts by influencing storm intensity, duration, and in some regions frequency characteristics. The exact signal can vary by basin and metric, but the physical direction is clear. When the fuel source warms and the water cycle strengthens, tropical cyclones can produce more extreme outcomes. Importantly, climate influence is not just about a higher top wind speed in isolated cases. It also includes slower moving systems in some scenarios, prolonged rain exposure, larger moisture transport, and repeated flooding stress on infrastructure designed for older climate baselines. So adaptation is not optional. Coastal defenses, drainage standards, building codes, emergency planning, and insurance frameworks all need to account for a risk landscape where historical averages are less reliable as standalone guides. Another common mistake is treating storm categories as full impact summaries. Category scales are useful for communicating wind thresholds, but they do not directly encode rainfall totals, surge geometry, storm size, forward speed, local topography, or infrastructure vulnerability. A lower category storm can still cause catastrophic flooding if it stalls or if it intersects saturated basins. A compact high-intensity cyclone can devastate a narrow corridor, while a broader but less intense system may distribute severe impacts across a much larger area. Decision-makers and households should read forecasts as multivariable risk portraits, expected wind field, surge zones, rainfall accumulations, river forecasts, and timing uncertainties. This more complete framing reduces false reassurance and supports better protective actions. It also helps explain why post-event assessments sometimes show damage patterns that seem disproportionate to category labels alone. The storm did not break the scale. The scale was never designed to represent every hazard dimension. Better public understanding starts with that distinction. So what should a practical mental model look like? Think of a tropical cyclone as an ocean-driven atmospheric machine that converts heat and moisture into organized rotation, violent weather, and concentrated hydrological stress. It forms where ingredients align: warm water, instability, moisture, low shear, and enough rotational support away from the equator. It intensifies through feedback between evaporation, condensation heating, pressure fall, and wind response. It impacts through multiple channels at once: wind damage, surge flooding, wave attack, prolonged rainfall, and sometimes tornadoes. It weakens over land in terms of core energy supply, yet inland flood risk can remain severe because moisture transport and watershed response continue. Under a warming climate, this system operates in a higher energy, higher moisture background, raising stakes for resilience planning. If you remember one thing, make it this: cyclone risk is not one number and not one coastline. It is a dynamic chain from ocean physics to atmospheric structure to human systems, and preparedness works best when we treat the whole chain as one connected problem. If you found this helpful, please like this video and subscribe for more explainers.